Hello, class. Today we'll continue with what we discovered about natural logarithms. So, we discovered that when we reflect the graph of e to the x, we ended up with the new graph, which looked like this, where this was 1 comma 0, and at e, that was 1, so this was e comma 1, and it got a vertical asymptote at what? X equal to 0. This was f of x is equal to ln x. Alright, so we discovered that log e is synonymous to ln, where ln has an invisible base e, that we normally don't write. So just as we did with common log, where the base was 10 and we don't write it, similarly in natural logs, we do not write the base e. We know that when we see ln, the base is always e. Okay, so just as we did with logs, we discovered some properties. Since log e is synonymous to ln, those properties should transfer to ln too. So let's see how that relates to ln. So I have ln 1. All right, so if you think about it intuitively, we are asking ourselves that invisible base e, to what power should we raise that e to give me 1? That is clear. It has to be 0. Let's do the work. So if I raise this to the power x, if I set it equal to the power to the x, equal to x, meaning that every log returns back to us an exponent that I'm trying to find, in this case x, then if I switch everything to an exponential form, that becomes e to the x is equal to 1, which now becomes very clear to us that x has to be what? X has to be 0. So ln 1 equal to 0 is a fact. We can always deploy this when we see ln 1. We can simplify that to 0. Now let's look at the next one, ln e. Again, we can intuitively see that when the base, which is invisible, is e, and we ask ourselves, to what power should we raise e to give us e? Clearly, the answer is 1. Let's do the work. Knowing that every log returns back to us an exponent, let's do the work. So that becomes e to the x is equal to e. Well, we got same base. The powers must be the same, so x is what? X is 1. So we are saying that ln of e is always equal to 1. That is another fact that you can always refer to. We also have ln e to the x. What is that equal to? Again, we are asking ourselves, if the base is e, to what power should we raise e to give us e to the x? The answer is clear. It has to be x. Let's do the work. Since I'm already using x, I'm going to set this equal to y, and let's convert everything back to exponential. So you get e to the y is equal to e to the x. Well, got same base. The powers must be equal, so y is equal to x. So we can say that ln e to the x is equal to x. That's another fact that you can always use. And then lastly, we have e ln x. What is that equal to? So now this is no longer a logarithmic expression. It's an exponential expression whereby e is the base and then ln x is the argument. Oh, sorry, is the exponent. My bad. That's the exponent. So that's the exponent, and that should return us back what? An argument. So let's say the argument is y. So then how do we change this to logarithmic? So to change it to logarithmic or natural log, or to log, this becomes log base e of the argument y is equal to ln x. Well, log e is the same as what we call ln, so that's ln y is equal to ln x. Well, if they're supposed to be equal, that means that these two must be equal. So y is equal to x. So in this case, e raised to the ln x must return us back what? X. So that is another fact. So if you look at the examples that they provided from the textbook, we're saying that ln e to the 8, that looks like which rule? That looks like this rule right here. So if I take that rule over there, it looks like the answer should be what? Should be 8, because it's ln e to the x and the outcome should be x. In this case, our x is 8. Well, if we look at ln 1 over e squared, we can rewrite this to give us ln e to the negative 2. And so we are asking ourselves to which of these rules is applicable here. Again, is this rule right here, that I got ln e to the power negative 2, the outcome should be what? Should be negative 2. Obviously, if it cannot be simplified algebraically, you can always rely on your calculator when you click on the ln feature on your calculator to solve. So just as they did in C, ln 5, I mean, you could convert it. So ln 5, we don't know what it is, but we know that we can convert it to e to the what? E to the x is equal to 5. It really doesn't help us because there's nothing to compare, but you can certainly use your calculator to evaluate ln 5. All right, so we can look at, before we get to domain, just like we did with logs, once we discover logs and we did the properties, we went straight to transformations. And like I said before, every function we discover, we'll look at its transformation. So we know the base graph of e to ln of x. F of x equal to ln x looks like this. This is 1, 0. E is E1. This is the graph of ln x. It's got a vertical lesson to add x equal to 0. So if I see this function here, 2 ln x plus 1, I know what's going on over here. I am stretching by a factor of 2 and moving this up by 1. So the graph of this function here is going to look like, so this point 1, 0, I'm going to stretch by a factor of 2, so I end up at 1, 0, and I'm going to move it up by 1, so that gives me 1, 1. And then e, 1, if I stretch it by a factor of 2, I get e, 2, and then if I move it up by 1, I get e, what? E, 3. Well, the vertical asymptote doesn't change, so it's going to stay exactly the same. But the point, my new point is 1 and 1, and then e is right here, and that's at 3, 1, 2, 3. So you get a graph going this way and going that way. Okay, let's look at another example. If I gave you f of x is equal to ln x minus 4 plus 2, then what's happening over here is I'm shifting to the right 4 unit and moving it up by 1. So again, if you look at your base function, which is ln x graph, if I look at the points, how the points are transforming, I get 1, 0. If I shift it to the right 4 places, I'm now at 5, 5, 0. And then if I move it up 2 places, I get 5, 2. Likewise, with e comma 1, when I move it 5 places, I get e plus 5, comma 1. And then if I move it up 3 places, I get 2 places, I end up getting e plus 5, comma what, comma 3. And also, what's going to happen to the vertical asymptote? That's going to change from 0, x equal to 0, to x is equal to what? X is equal to 4. So when I sketch that graph, I got a vertical asymptote at 4. I got 5 and 2. Okay. And then I also have, which one? E plus 5. So E is 2.7. So 5 plus 5 will put it as 7 point something. So 1, 2, 3, 4, 5, 6, 7, a little bit after 7. And then go up 3 places. So that's 3, 2, 1. So the graph looks like something like this. All right. And in both cases, these are all sketches. So, okay. So that's an example. You could certainly do a reflection. So if you have f of x is equal to ln negative x, then that's a graph that is reflected about the what? About the y-axis. So from your base graph, this is going to look like that, where this is negative 1, 0, and then you have negative e to the what? To the 1. If this is 1, and that's e negative. Okay. And likewise, lastly, I mean, you could do so many things, but I hope this gives you a clear idea with where I'm trying to go with this. That you could do any form of transformation that you want to do with ln x. Okay. Lastly, let's return ourselves back to domain of logarithmic functions. So the same process as we did. If you look at the basic graph of ln x, the domain is always x greater than 0. So everything that we did with finding the domain of a logarithmic function applies to ln x. So in this case, I have ln 4 minus x, and I want to find the domain. I'm going to try and set 4 minus x squared greater than 0. If I solve this, I get 2 minus x, 2 plus x greater than 0. My zeros are negative 2 and 2. If I put it on the number line and I test it out, I can see that if I make x bigger than, if I pick an x value greater than 2, it makes this region here negative. If I pick anything between negative 2 and 2, that makes it positive. If I pick anything less than negative 2, if I pick up anything between negative infinity and negative 2, say pick up negative 5, that makes this region negative. So the only place where this equality is going to be true is when x is between negative 2 and 2. Okay, so same things carry over in logs and natural logs. Okay, thank you for watching, and hopefully the worksheet or the homework is easier by watching this video.